Today we're going to take a look at 7.6, the natural base e. E is an irrational number just like pi, but it's a number that we use quite a bit when we talk about some exponential growth and decay situations. You can find e on your calculator in two spots. One is right above the division sign, and the other one is right above the button that has ln on it, which we're going to talk about what that means today as well. The ln button is right underneath log. If you type in e on your calculators, you're going to find out that it comes out to be 2.71828, which that on your calculator may look like it's a repeating number, but it is an irrational number. It does not actually repeat. E can be derived from our compound interest formula, the A equals P times 1 plus R over N raised to the NT, where if we take and say that we invest $1 for our principal at 100% interest rate, so R is going to be 1, and we just compound it so many times for 1 year, we're going to get a formula that looks like this. And as you pick numbers for n, and they get bigger and bigger, so let's say we say it gets compounded daily, so we're going to put in 365. If we plug this number in, we get 2.715 approximately, which is close to E. If you pick bigger and bigger numbers for n, you're going to find out that it gets closer and closer to E. So this graph itself is going to get closer and closer to a value of E, which is our definition of an asymptote, and it's going to have this horizontal line that is going to get closer and closer to, but never going to reach. That value that it comes out to be is E. We use E in a lot of exponential growth and decay situations. There's one word that we're looking for to tell us that we want to talk about E, and that's going to be the word continuously. Anytime that we see that word there, it's going to tell us that we want to use a different formula than the basic exponential A times B to the x power. So that actual formula for continuously compounding something is A equals PE to the RT. A is still your total amount, P is still, in this case, your principal, R the interest rate, T is your time. But we have to use something different because we're talking about compounding it continuously. And anytime, again, that you see this word here, think about the word PERT. This is an easy word to remember. Continuously goes with PERT, and then you can take that to derive the PE to the RT. So the first problem we're going to take a look at is what is the total amount for an investment of $1,000 invested at 5% for 10 years compounded continuously. There's the key word continuously telling us that we need to use the PERT formula. So A equals PE to the RT. We fill in the amounts that we know. Total amount we're trying to find, that's A, so we leave it as A. $1,000 investment, what we start with is the P. 5% in interest rate, so 0.5 is the R, and then 10 years, that's going to be the T. That, if we take a look, it's just 1,000 times E, which E is just a number, raised to the 0.05 times 10. We can type that onto our calculators, and when we type that in, we should get 1648.72, and it becomes $1,600 after 10 years. To take a look at it from a different situation, let's say it was only compounded twice a year, meaning that we would use the A equals P times 1 plus R over N raised to the NT. If we only compounded it twice a year for that same time, it would be 1,000 times 1 plus 0.05, only compounding twice a year, so 2 raised to the 2t, where the 10 years would actually then be 10. If we were to plug this in to our calculators, we would get 1638.62, which we have talked about in the past. The more times that you compound it, the little bit more money that you're getting. That here we're compounding continuously, we're actually making a little bit more money than what we made down here. Now, we don't have to just use this PERT formula for interest rates. We can talk about it really for any situation that is going to represent continuous growth or decay. In the case of the interest rate, that was continuous growth. Here we're going to take a look at it, one that's going to be continuous decay. So technetium-99m, a radioisotope used to image the skeleton and the heart muscle, decays at a rate of negative 0.1155. First question, why is this rate negative? Why are we going to see a negative number here? Is because really we're decaying. We're decaying, so we're losing an amount, so that exponent that we have is going to need to be negative. So let's actually use this to determine how much is going to be left after 24 hours. So we're going to go A equals PE because we're raised to the RT because we are dealing with continuous growth and decay. The initial amount that we started with is 250. E raised to our rate is negative 0.1155, and our time is going to be 24 hours, which we can put in 24 because it's saying that our rate decays per hour, so we really want that time to match that up. And again, this is just something else since we have all numbers over here. That E again being a number, we have all numbers, we can just type it into our calculators, and we should get 15.63 when we're all said and done. So we'd have 15.63 milligrams left after 24 hours. Since E is just a number, we can talk about it as being an exponential function, as an E raised to the x power. If we go with e to the x power as an exponential, it's going to follow all the other properties that an exponential function has, as in it's going to cross the y-axis at 1 if it's just e to a power, just like 3 to a power. It's going to have the same exact pattern as a growth function because e is a number that is bigger than 1. Remember, this value here represents our growth factor, and any number bigger than 1 is growth, any number smaller than 1 is going to be decay. So it's still going to represent growth, meaning that it's going to move up like this. It's also still going to have the same kind of asymptote as what this graph would have. It's going to have an asymptote at y equals 0. The domain is still going to be all real numbers. The range is still going to be y is greater than 0 because that e value is 2.71. So it's still going to have all those same properties. And again, it should model exponential growth because our growth factor is greater than 1. Well, since we have this being an exponential function, that means we also have its inverse, which would be a logarithmic function. The inverse of e to the x power, as in y equals e to the x power, the inverse is going to be log base e of x. But anytime that we see this log base e here, we don't actually write it out as log base e. We call it a natural logarithm. And our short way to write out natural log is ln. That's that button on the calculator we talked about right at the beginning. Is natural logs have the exact same properties as logs with base 10 and log with other bases. It's still going to have, in this case, it's still going to have an x-intercept of 1. It's going to follow the same exact shape of every log function, and it's going to have an asymptote at x equals 0. The domain would just be greater than 0 then, since the graph can't cross at x equals 0. The range in this case, the y values that it can be, would be all real numbers. Here's the really nice thing about the natural log is everything that we have learned from 7.4 of the different properties that you have with logs and 7.5 of being able to solve equations with logs, all of that stuff applies to natural logs. It's not going to be any different. So let's take a look at some problems in terms of being able to solve things with natural logs. So example A here, the natural log of e raised to the negative 2t. If we want to try to simplify this thing down, the first thing that we may see is that we have an exponent inside our natural log, which we can do the same thing with the exponent inside the natural log as we can with the ones as exponents just inside logs. We can take that exponent, we can move it out in front, so it becomes negative 2t multiplied with the natural log of e. This natural log of e, remember, the natural log is just a log with base of e, so natural log is log base e, and there's the e inside the natural log, which, if we remember from before, we have a base of e, and we have e inside that log. When you have these two numbers are the same, what does this thing come out to be equal to? It's going to be 1, so negative 2t times 1 means this thing is equal to just negative 2t. If we take a look at example B, we have e raised to the natural log of t minus 1. We may not know how to simplify this one out, but we take a look and say, hey, it's equal to x. What form is it written in? It's e to a power. Even though there's a natural log there, it's just e to a power, so it's an exponential form. If we don't know what to do, we can change it out of exponential into logarithmic form. So we can go log with our base, which in this case is going to be e, and then we can follow the circle method. So that's going to be of x raised to, or equals, what is raised to the natural log of t minus 1. Which log base e is just the natural log, so we get the natural log of x equals the natural log of t minus 1. We have these same natural logs here, which means that x should just equal t minus 1, so our answer that we're looking for is t minus 1. For C, I'd like you guys to attempt this one on your own for homework. The answer that you should get for this, when we're all said and done, would just be x raised to the 5th power. Alright, let's take a look at ones that we actually have to go through and solve. So natural log of 5 plus the natural log of x equals 1. First thing we want to talk about is we see two natural logs here, so we'd want to try to simplify this down by combining them into one natural log. Which, can we combine these two? We can. They have the same base. So we look at the sign that's in between them. Remember, with two logs, if they were the same base, we could add them by multiplying the two values inside the logarithms. So with natural logs, we can do that same exact thing. We can multiply the two values inside, so it becomes 5x equals 1. We have a single logarithm now, or single natural log. We can't simplify this anymore, so once we get it down to as much as we can simplify it in that form that it's in, we want to change this to exponential. What's our hidden base that we see? It's not 10 this time, because it's a natural log. The hidden base that we have is e. So we can rewrite this to be e raised to the first power equals 5x. So e raised to the first power equals 5x, which this is really just e. So then let's go through and actually solve for x now. Divide both sides by 5, and we would get x equals e over 5. We can leave our answer as that, or we can type it in and say this is going to be approximately equal to 0.545. All right, B, I'd like you guys to go through and again attempt this one for homework. Your answer that you should get when you're all said and done for x is 5 divided by e to the third, or if you divide that out, approximately 0.249. All right, let's take a look at C. We want to try to go through and solve this one for x. We only see one log, so we can't really go through and combine these two values. But we may see that there's a number outside in front of the log, so we may want to do something with that, or we may want to do something with this -2. There's a couple different ways that we can go through to be able to solve this. Maybe the first thing we want to take a look at is see that we have a -2 here, so let's just add 2 to both sides. So we get 2 times the natural log of x equals +2, and then the next thing we can do to simplify this down, we can get rid of this 2 one of two ways. Since it's a 2 that's just out in front, we can either take it, move it up in front of the exponent so it just becomes a single natural log, or we could just go through and divide both sides by 2 to be able to get the natural log of x equals 1. And now it's just a matter of saying let's rewrite this. What's our base that we don't see here? Since it's a natural log, that's going to be base e, and we could just change this into exponential to be able to finish solving it. E raised to the first equals x, so that just means x is equal to e. For D, 4 natural log of x minus the natural log of x to the fourth. There's a couple ways again that we can do this one, but we have two natural logs that we may want to try to go through and combine. Well, we can't combine them until they're just natural logs, so this 4 is creating an issue. We can take it, we can move it up in the exponent. It becomes the natural log of x to the fourth minus the natural log of x to the fourth equals 0. Now, there's two ways to be able to combine this from here. Is we have two natural logs that we're subtracting, so maybe what we want to do is take those two x's and divide the two x's. Or we could take a look and say it's just the natural log of one thing minus the natural log of the same thing, since we're subtracting the exact same thing, whatever this value is and whatever this value is. Since they are the exact same thing, this minus this is just equal to 0. Which, if we have 0 equals 0, that's an example that we have, which we could say would be all real numbers. But we want to take a look at what this means, all real numbers. That means that we can put any value that we want into this equation for x. But the original problem that we started with was 4 multiplied with the natural log of x. And if we think about our domain could only be values greater than 0, which means we are only allowed to use values of x that are greater than 0. So even though it's all real numbers as our answer, we can't put all those numbers in for x. We can't take the natural log of 0, we can't take the natural log of negative numbers, hence the domain being x is greater than 0. So, since we can't use negatives and we can't use 0, our answer really is going to be x is greater than 0. It's not actually going to be all real numbers. Now, if you wanted to for this one, you could go through and say I have two natural logs that I am subtracting here, so let me divide those two things. The natural log of x to the fourth divided by x to the fourth, which x to the fourth divided by x to the fourth is 1, so it's the natural log of 1 equals 0, and we could rewrite this e to the 0 power equals 1, which e to the 0 is just 1, which means this thing really just becomes 1 equals 1, which would be the same exact situation here as what we got here. So really there are multiple ways to be able to solve these kinds of problems when you go through and you see them written that way. The last one for E, I want you guys again to attempt this one for homework, the answer that you should get when you're all said and done is 2. To help yourself out with this one, when you see e to the natural log of x to the third, I would like you to take a look at this example here, because we have something very similar in this one as what's happening down in e. How do we do this one? You can do this one the same exact way. All right, the last one that we're going to take a look at is this problem down here, just being able to go through and solve this one. It's another investment problem. There's your word there, continuously, meaning that we want to use the PERT formula. So A equals P e to the RT. I would like you guys to do this one for homework as well. The answer that we should get when we're all said and done is $9,465.87. All right, and that's where we're going to stop.